be amplification and also the modulation technique here. Now let us look into the some of the course content of the digital signal processing as per the VTU. The subject code is 18 EC 52. So it's a 18 scheme, and in the fifth semester it's a second subject. So let us look into the course content of the digital signal processing. So I'll give the overall view of the overview of this subject, digital signal processing. So in this subject we are going to study the basic operations of the signals, we are going to consider the discrete Fourier transform. So which is the thing, but it's a modified version of the Fourier transform that is called as a discrete time Fourier transform. So we are going to call that as a discrete Fourier transform. And for that one, we are going to see some different methods of finding the discrete Fourier transform by using the methods by using the linear transformation, by using the matrix method, and by using the formula method. We'll see that one. Afterwards, we are going to see some of the properties of the DFT. So DFT is having around some 10 to 12 properties are there. We are going to look into the properties of the DFT. Afterwards, we are going to see the linear filtering technique in this one, and we'll go for the FFT algorithm, that is the efficient computation of the DFT. It's a modified version which you can save the time required for calculating the DFT, so we go for the FFT. Afterwards, we are going to look into the design of the filters. The two kinds of filters are there. One is called IAR filter, FIR filter, and we are going to see the realization of this discrete time filters. And later we are going to look into the digital signal process, the basic structure of the digital signal processor we are going to look here. So this is a overview of the subject. So to be summarized within the 2 or 3 lines, we can say the DSP, we are going to look into the DFT and its properties, and the FFT, and the design of the filters, and the architecture of the DSP processor. And the prerequisite for this subject is, so the students already, the students have come across the signals and systems. They should know the some of the basic concepts of the signals, and also along with the signals and systems are required. So along with that one, they should know the mathematical operations like integration, differentiation, and finding the energy of the signal, power of the signal, and the many aspects it is required for the as a prerequisite for the this digital signal processing. Now let us look into the course content of the DSP. So in the contents, in the module 1, we are going to see the discrete Fourier transform. So in the signals, we have come across the discrete time Fourier transform. The meaning of discrete time Fourier transform is the thing, but for the kind of discrete time signals, if you're going to find the Fourier transform, you're going to call it as a discrete time Fourier transform. So the one of the advantage of the discrete time Fourier transform is the signal in the time domain. It's a non-periodic signal and it is a discrete time signal. When you take the Fourier transform of that one, so it will become the discrete time Fourier transform. The signal we are going to get, the periodic spectrum you are going to get in the frequency domain. That periodic spectrum is continuous with respect to the frequency, but it is not discrete. So for that one, the time domain it is discrete, but in the frequency domain it is continuous, and also it's a periodic one is there. But for the signal process, which we are going to use a digital computer or the digital signal process. So in order to perform the operation on the signal should be discrete in the time domain, and also in the frequency domain also it should be discrete is there. So the DTFT is not a efficient tool for the performing the operation by the DSP process or the computers. So we are going to derive the new formula. The formula is called as a discrete Fourier transform. So as the name indicates, discrete Fourier transform. So in the frequency domain, the signal will be discrete will be there. In the time domain also the signal will be discrete is there. The corresponding transform you are going to call it as a discrete Fourier transform you are going to call. And that one you are going to study as a first topic in the module 1. So where we are going to consider the DTFT of the non-periodic signal we'll consider, and for that one you're going to perform the frequency domain sampling, okay, and in order to obtain the formula for the discrete Fourier transform. Later we'll do the reconstruction of the signal. That is, once we find out the discrete Fourier transform, we need to find out the inverse discrete Fourier transform. We need to find out. So that one you're going to look into the as the first topic in the module 1. Afterwards, we are going to see some. We are going to introduce the modified the formula, and we are going to introduce some modified formula for the DFT. And for that one, we are going to introduce a new factor, which is called as a Twiddle factor. So that one will be done as a simplified formula for the DFT. Afterwards, we are going to use the DFT as a linear transformation. Linear transformation is the thing, but we are going to express the discrete Fourier transform formula as a set of linear equations, and it will be expressed in terms of the matrix format we are going to express. So we are going to find out the DFT by using the matrix method, and also the inverse DFT we are going to find out by using the matrix method, and we are going to find the concept of finding the IDFT by using the DFT you are going to use here. Means to find the IDFTs of the signal, we are going to use the DFT formula. So that one you are going to study in the module 1. Afterwards, you are going to look into the some properties of the DFT. There are around some 10 properties are there. So among that one, so what are the properties applicable for the DTFT? The same property is applicable for this one also, but only change is the in the frequency domain, the signal will be discrete in nature, and in the time domain also the signal will be discrete in nature. So that one we are going to see. So some of the properties are, it's a periodicity property, linearity, the symmetry property, and also the multiplication of the two DFTs you are going to see, and you're going to see the circular convolution of the signals and many additional properties you are going to look. So these are the things you are going to study in the module 1 as a CO1 we are going to obtain here. So to summarize, in the module 1, we are going to derive the formula for the DFT, and we are going to see the different method of finding the DFT of the any signal, that is by using the matrix method, and we'll see some of the properties of the DFT. You are going to look into that one. So if you come to the module 2, in the module 2, we are going to continue with the some of the few properties of the DFT you are going to continue. Afterwards, you are going to use the DFT for a linear filtering applications. So usually the linear filtering is the thing, but so the filter which is going to satisfy the property of linearity and time invariance, you are going to call it as a LTI system you are going to call. So for that one, the input will be X of n will be there. The system impulse response will be H of n will be there. For that one, you are going to find the output as a convolution of the input with the impulse response of the system you are going to consider. So that one you are going to call it as a linear filtering you are going to call. So in order to find the linear filtering application, for, that is in order to replace the equivalent one for the convolution, we are going to use the DFT by means of using the circular convolution, or by means of using the DFT and FDFT, we are going to find the linear filtering methods. So there are two methods are there. One is called as the overlap save method. Other one is the overlap add method. So these are the two linear filtering techniques we are going to use for the filtering of the long data sequences. Afterwards, we are going to look into some of the problems on the linear filtering techniques. We'll look here. Afterwards, we are going to see find out the number of calculations involved in finding the DFT. For example, in the DFT, there are a lot of operations are involved. For example, it may be the addition, multiplication, and evaluation of some trigonometric functions or the exponential functions. So, and also a lot of shifting and additional operations are involved here. So we are going to find out how many calculations are involved in the this DFT, direct computation of the DFT we'll see here. And since the number of operations are more, we are going to reduce the number of operations by introducing a new algorithm which is called as a fast Fourier transform algorithm. So what we are going to do is, we have the two different methods are there. One is called as a that is a radix2 method we are going to call. Radix2 is a thing, but so it is we are going to express the capital N point DFT we are going to express as a 2 to the power of n. That's why it is called as a radix2. We have the two methods among the radix2. One is called as a decimation in time FFT. Other one is called as a decimation in frequency FFT algorithms. So by using these two, we are going to find out the DFT of the sequences. We are going to find out. We are going to derive the algorithm for that one. And in this one, in order to reduce the calculations, we are going to make use of the some two properties of the Twiddle factor we are going to make use. So those properties are nothing but the symmetry property and the periodicity property. So by using that one, we are going to reduce the number of calculations. So these things we are going to study in the module 2, and we are going to introduce the efficient computation algorithm, which is called as the fast Fourier transform algorithm. And this will reduce the number of mathematical calculation it will reduce. So if you come to the module 3, in the module 3, we are going to look into the so some design of the filters you are going to look here. So the filter is nothing but it's a device which is going to remove the unwanted signal. So that one you are going to call it as a filters you are going to call. Among that one, design of the filter is the thing, but we are going to find the impulse response of the filter, that is called H of n. We are going to find out. So if the H of n is finite one, we are going to call it as a finite impulse response filter we are going to call. And if the impulse response is infinite, we are going to call it as a infinite impulse response filters we are going to call. So in this model, we are going to consider the finite impulse response filter we are going to consider. Okay. So for that one, we are going to look into some of the characteristics, like if the H of n is symmetric, and if it is H of n is asymmetric, antisymmetric about the midpoint, we are going to consider the characteristics of that one. And we are going to consider the design of the linear phase filter. The linear phase is a thing, but if the impulse response is symmetric or antisymmetric about the midpoint, we are going to call it as a linear phase FIR filter we are going to call. And in order to design the filter, we are going to use the windowing techniques we are going to use. So windowing techniques is a thing, but the impulse response H of n, which is infinite in nature, that one you are going to multiply with the finite impulse response windows you are going to multiply, and we are going to get the finite impulse response FIR filters you are going to get. So we have some 6 different types of windows are there: rectangular window, Hamming window, Hanning window, Bartlett window, Blackman window. These are the different types of windows we are having. We are going to see the design procedure for these FIR filters you are going to see. Afterwards, we are going to look into some practical problems by considering the different parameters. We are going to find the design the FIR filters for the different applications we will see. Afterwards, you are going to look into the other method of designing the FIR filter by using the technique called as a frequency sampling technique. So frequency sampling technique is nothing but we are going to take the Fourier transform of the impulse response. For that one, you are going to perform the sampling you are going to perform in the frequency domain, and that for sample signal we are going to take the inverse impulse inverse DFT you're going to take, so that you are going to get the H of n, that is called as a frequency sampling technique here. We are going to use that method to find the design the FIR filters. And afterwards, at the end, we are going to look into the some of the structure of the FIR filters. That is, we are going to implement the filter by using the discrete time structures. One is called as a direct form. One direct form, two structures are there, and the cascade structures, and also the look into the lattice structure. So the advantage of the lattice structure is, suppose if you want to increase the hardware order of the filter, so directly we can cascade the filters. So that is the lattice structure. That's the advantage of the lattice structure. And this is things we are going to see in the module 3. In the module 4, if you look into the module 4, we are going to look into the design of the IR filters. We are going to consider design of the IR filters, which is impulse response is infinite impulse response is there. So there we are going to have the two different types of filters are there. One is called as the Butterworth and Chebyshev filters. First, we'll look into the design of the unlocked Butterworth filter by considering the unlocked filter specifications. So we are going to find out the normalized Butterworth filters we are going to find out. So then that filter we are going to convert into the digital form by using the bilinear transformations. Okay, so this is one of the method which can be used to convert the continuous time, that is unlock filter, into the digital one by means of using the bilinear transformation. So next we are going to look into the design procedure for conversion, and we're going to look into the structure of the realization of the IR filters by using the direct form and direct form 2. We are going to look into that one. So these are the things we are going to study in the module 4. So well, if we come to the module 5, we are going to expose to the that some of the parameters related to the digital signal process. Like we are going to look into the architecture of the DSP, and some of the hardware units such as the arithmetic and logic unit, and the multipliers. We are going to look into that one, and we are going to see the different formats of the hardware unit, which is called as fixed point format and floating point formats. You are going to look into that, and we are going to see the fixed point digital signal process and also that one, and we are going to consider the design of the FIR filters and IR filters in the fixed point systems. You are going to look into that one. So these are the 5 different models where we are going to expose to different type of concepts. So first module we have seen the DFT and its properties. Second module we have reduced the number of calculations by using the FFT. Module 3 we are going to look into the FIR filter design. Module 4 we are going to look into the IR filter design. In the module 5 you are going to look into the practical digital signal process and its architecture. And these are the textbook as I discussed in the lecture 1. So these are some of the textbooks you are going to use. Among this one, this is a textbook is good one. And the reference book, Discrete Time Signal Processing, where the theoretical concepts has been given nicely. And the reference book to Sanjit K. Mitra book. So where you are going to have a lot of mathematical expressions, lot of MATLAB programs are there for each and every applications. And Lee 10 is this book is also very good. And we have the wide exposure to the DSP topics and as well as the concepts. So these are the contents of the DSP. In the next section, we are going to look into the frequency domain sampling of the DTFT in order to obtain the DFT formula. So you're going to look into that one in the next session, in the lecture 3.